Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is your instructor Anisa Nawaz from Department of Physics. This is our lecture number 23 from chapter number 2, Vectors and Equilibrium. In the previous lecture we have discussed about equilibrium and conditions of equilibrium in detail. We were having two conditions of equilibrium which must be fulfilled for the complete equilibrium of a body. In today's lecture, we will discuss about numerical problems related to equilibrium. Before moving towards the example and assignment related to equilibrium, let's first discuss figure 2.34 in your book, page number 65. So you can see we are having this figure in which we are having, let's say, a body in this shape. You can see that we are having axis of rotation. This is given as axis of rotation and different forces are being applied on this body. You can see this force is applied in the upward direction, this force is applied in the upward direction, and this force is applied in downward direction. So you can see that upward forces are balanced by the downward forces. So what we can say, according to first condition of equilibrium, sum of all the forces must be 0. You can see over here that by convention upward forces are taken as positive and downward forces are taken as negative. Keep this in mind that by convention we take upward forces as positive and downward forces as negative. So over here 2f minus 2f, that will give us 0. First condition of equilibrium is satisfied. If first condition of equilibrium is satisfied, it means that this body is in static equilibrium, means you can say that there is no linear acceleration. And if you are talking about second condition of equilibrium, you can see over here that if this is the pivot point, this is the pivot point, this is axis of rotation, then there is no tendency of rotation as well. Clockwise torques are balanced by anti-clockwise torque. Okay, so this body is in static equilibrium. We will say that second condition is also satisfied. So we will say that if first and second condition both are satisfied, then the body is in complete equilibrium and there is no tendency of linear as well as angular acceleration. Okay, so this body will have no linear acceleration, no angular acceleration, so it will neither move, it will neither follow translational motion or it will not rotate. If we consider second figure over here, you can see that upward force is equal to the downward force. Upward force and downward force are balancing each other. So we can say that first condition of equilibrium is satisfied. This body is having no tendency to move. This body is having no tendency to follow translational motion. Okay, because net force in this case is 0. If we are going to check out second condition of equilibrium, if this is the axis of rotation, you can see that over here this force is applying a torque and this force is applying a torque, and these two torques are not balanced. Okay, so we can say that second condition of equilibrium is not satisfied. Sum of all the torques is not 0, so this body is having a tendency to rotate. First condition is satisfied but second condition is not satisfied, so this body is not in complete equilibrium. It will start rotating in clockwise direction. You can see over here it will start rotating in clockwise direction. And if we are considering this body, you can see over here we are having one force in this direction and the other force in this direction. So these two forces are producing opposite torques. So we can say that second condition is satisfied but upward forces are not balanced by the downward forces. So this body, what will happen, this body will move in upward direction. First condition of equilibrium is not satisfied, so this body will having a net upward force, so body will start moving upward. Okay, and second condition is satisfied. You can see over here, if we are multiplying this force tau is equal to r cross f, this will give us rf, and over here tau is equal to half r into 2f, again it will give us a result rf. Okay, so rf is balanced by rf, both torques are equal in magnitude but opposite in direction, so second condition is satisfied. So hence this body is not having a tendency to rotate, but it is having a tendency to follow the linear path. Okay, so if we are going to find out the torque in a specific direction, what we have to do, you can check this out. If we are having this figure and we want to find out, let's say that we have to apply conditions of equilibrium on this figure. Okay, so you can see over here, right now we are having this board, let's say we are having this board or bridge, whatever you say. So this board is being applied by 4 forces. You can see we are having Fa, which is acting in upward direction. We are having a weight of this person acting in downward direction. We are having a weight of this bridge or this board which is acting in downward direction, and we are having you can say reaction force applied by this support, which is again in this upward direction. Okay, so Fa and Fb are in upward direction, and weight of the person and weight of the board is in downward direction. So if we are going to apply first condition of equilibrium, if you are having any object, if you are having any body, any figure like this, then what you will do, if you have to apply first condition of equilibrium, then you will write sum of all the forces acting along x-axis. You can see there are no forces acting along x-axis, so that will be 0. Sum of all the forces acting along x-axis, that will be 0. But if we see the sum of all the forces acting along y-axis, Fa and Fb, they will be written with plus sign. Fa plus Fb minus W1 minus W2. Okay, so Fa and Fb will be written with plus sign, and these two weights acting in downward direction, they will be written as minus sign, and sum of all the forces will be 0. Why 0? Because this bridge is in equilibrium, it is not moving. So what will happen, we have to apply first condition by taking sum of all the forces. And if we have to apply the second condition of equilibrium, for second condition of equilibrium, which is sum of all the torques acting on a body must be 0, what we have to do, the first step should be that we have to consider a pivot point, we have to consider an axis of rotation. It's up to you which axis of rotation you are considering, but you have to check this out, that you will use most appropriate axis of rotation so that calculations become easy. It doesn't matter which axis of rotation you are taking, but when you will take, let's say that we are considering this point as axis of rotation, then what will happen, this force Fa will not be able to produce any torque because it is having no distance. Distance is 0. Tau is equal to r cross f. R is 0 in this case because force, line of action of force is passing through axis of rotation. So this force is unable to produce any torque. So we will ignore this force. Okay, while writing the sum of all the torques, we will ignore this force Fa, because we have considered this point as axis of rotation, and this line of action of this force is passing through axis of rotation, so it will not tend to produce any torque. Then we will move towards this weight. You can see it is having a specific distance which is given as 2 meters. So this R is R or L, whatever you say, this is 2 meters and force is 750 Newton. So what we will do, we will separately find out torque due to this force, 2 meter multiplied by 750 Newton. So this will be the torque due to this weight. Again, we will check out the distance of this point from axis of rotation. Distance of this point from axis of rotation will be You can see total length of this bridge is 12 meters, so half length will be 6 meters, because weight center of gravity of this bridge is lying at the center. So what we will say that this distance is 6 meters. Okay, so what we will do, we will use R as 6 and force will be 500 Newton. So 500 into 6 will be the torque applied by this force. Then we will move towards this force FB. We will check this out. If we consider the torque applied by this force, then what will be that? We will multiply the total distance from axis of rotation to this point, that is 12 meters, multiplied by this force. So 12 multiplied by FB. So we will take sum of all the torques must be 0. But we have also considered another point, sign convention. So we have considered this thing that those torques which are in clockwise direction are taken as negative, and those torques which are in anti-clockwise direction are taken as positive. So how we are going to find out that which torque is clockwise or which is anti-clockwise? Let's say we have considered axis of rotation at this point. Then we will place thumb of our right hand on this axis of rotation and we will curl the fingers in the direction of force. That will give us the direction of torque. So our fingers for this force will curl in clockwise direction. So this will be having a negative sign. Again clockwise torque, a negative sign, and this one is in anti-clockwise direction, so it will be with positive sign. So you should keep all these points in mind before solving examples or numericals related to equilibrium. So now let's move towards example 2.5, page number 66. Statement of that example is: Hina weighing 450 Newton is standing at the edge of the uniform diving board 5 meters in length. Weight is given, length is given. Weight of the board is 150 Newton and is bolted down at the left end. At one end it is bolted down, okay, it is fixed, while being supported 1.5 meters away by a fulcrum as in figure. We will check out the figure. Find the forces that the bolt and the fulcrum exert on the board. Okay, right now we have to find out two forces, two unknowns are there, bolt and the fulcrum, the forces which bolt and the fulcrum are exerting. So a simple point should be there that if we are having two forces, then we have to use two conditions of equilibrium. Okay, two unknowns are there, so two conditions of equilibrium are applied. Over here you can see we are having this figure, we are having a diving board and Hina is standing over here at this end. Force or the weight of Hina is FH, it is represented by FH, which is 450 newtons. Weight of the diving board, it is represented by FC, center C. Okay, FC is equal to 150 Newton, again acting downward. This is bolted at one end, fixed at one end. Okay, and we are having a force FB over here in this direction, let's say, and we are having this fulcrum which is applying a reaction force in upward direction. This force due to fulcrum is unknown and force due to bolt is unknown. Okay, and distances are also given over here. Distance of fulcrum LF is 1.5 meters, distance of center LC is 2.5 meters, and length of the board LH is 5 meters. Okay, so we will write all these values in given data. So let's write it. In given data, what we have to do, we will write down a weight of Hina given, FH is equal to 450 newtons. A weight of board again given, which is 150 Newton. You can see in this figure as well. Weight of Hina 450 Newton, weight of board which is 150 Newton. Weight of Hina is 450 Newton. Okay, center of gravity LC is at a distance of 2.5 meters. Distance of fulcrum is 1.5 meters. Length of the board LH is equal to 5 meters. And what we have to calculate, required value is force FB and force FF. Okay, force applied by the bolt and force applied by this fulcrum. These two forces are unknown. So obviously if this is the question of equilibrium, so we have to apply conditions of equilibrium. Okay, so what we will do, if we are applying first condition of equilibrium first, then what will happen, we have to take sum of all the forces in upward direction and downward direction. Okay, so here we will be having two unknowns. If we are applying first condition first, then we will be having two unknowns and we cannot solve it. So what we will do, we will first apply second condition of equilibrium by taking axis of rotation at this point. Then what will happen, this force will be vanished, because line of action of force will be passing through the axis of rotation. So what we will do, we will find torque against all other forces and we will find out the unknown force Ff. Okay, so let's check out how we are going to do that. First point is we have to consider an axis of rotation, and right now let's say we are considering axis of rotation at this point at bolt. Okay, it's up to us that which point we are considering at as axis of rotation, it doesn't matter. So right now we are considering this bolt as axis of rotation. For the axis of rotation of our pivot point at A, what will happen, let the torque produced by support fulcrum is tau F, the torque produced by weight of board is tau C, and the torque produced by weight of the girl Hina is tau H. We are giving them the name tau F, tau C and tau H. So what we will do, we will apply second condition of equilibrium over here. Sum of all the torques is equal to 0. So therefore what will happen, you can see over here, if this is the pivot point, this is the axis of rotation, then what will happen, this Ff, basically torque due to this force is in anti-clockwise direction, so this will be positive. The torque due to this force, this is in clockwise direction, so it will be negative. Torque due to Fh will be again clockwise, so that will be negative. So what we are using positive sign with tau F and negative sign with tau C and tau H. Okay, so we have to use this sign convention. This is very important. Without that we will not get the right answer. The sign convention is adopted, hence what we will do, we are just putting the value of tau is equal to Rf or Lf or Fl. We are just using the magnitude. Representation could be anyone. In your book it is given as L, so we are using L over here instead of R. It doesn't matter. So as we know that the formula of torque, tau is equal to Lf over here, so we will use subscript F for fulcrum, Ff, Lf, which is the torque produced by the fulcrum. C is for center, Fc, Lc, and H for Hina, Fh, Lh. Sum of all the torques is equal to 0. So if we are having this formula, then what we will do, we will take these two parameters on the other side of equality, so they will become positive. Minus sign will be converted into positive sign when these values will be taken on the other side of the equality. Okay, you can see over here Ff, Lf is equal to these two values with positive sign. Then we have to separate this Ff, this unknown value. Ff is unknown value, so we have to separate it out. You can see over here we have divided with Lf on both sides. This Lf will be cancelled and we will get this result. By dividing Lf, by separating Ff, we will get F is equal to this whole value divided by Lf. Okay, and name it as equation number 1. So by putting values in equation number 1, all these values are known, these are given, so we will put all these values in equation number 1 like this with the units. Okay, with you can see we are solving it step by step and we will get this result, 1750 Newton. So force due to the fulcrum is 1750 Newton. Okay, so first value is calculated, first unknown is calculated by using second condition of equilibrium, by using axis of rotation at bolt. Okay, now for force Fb, the force due to bolt FB can be easily found out by solving first condition of equilibrium along y-axis. We can see there are no forces along x-axis, so there is no need to apply that condition. Just apply the first condition of equilibrium along y-axis such that sum of all the forces acting along y-axis must be 0. Okay, and we have to use the convention that upward forces are with positive sign and downward forces are with negative sign. You can see that only FF is in upward direction, so FF is with positive sign, while FB, FC and FH are in downward direction, so they will be taken with negative sign. Okay, sum of all the forces must be equal to 0. Okay, and we know that the unknown force is FB. We have calculated FF with the help of the second condition of equilibrium. Now only unknown is FB, so we will separate this FB, and all the rest of the terms they will move on the other side. Okay, so FB is equal to FF, sorry, this should be plus FF plus FC plus FH. Okay, so they name it as equation number 2. So if we are putting values in equation number 2, then what will happen? We will get the result 1150 Newton. So this one is the second unknown. FB is 1150 newtons. Okay, we have calculated unknown value over here. Both forces are calculated by using both conditions of equilibrium. Now if we move towards assignment 2.5, statement is a uniform plank of weight 200 Newton and length 6 meters is supported by a rope as shown in figure. If the breaking tension in the rope is 400 Newton, how far can a boy of weight 400 Newton walk towards the support? What they are saying, we are having a uniform plank, weight of the plank is 200 Newton, tension in the string which is attached on the other end, that is 400 Newton. Okay, a boy is walking on the board which is having weight of 400 Newton, so they are saying that this boy is walking towards this end. Okay, there will be a certain point after which that certain point that will be known that will create breaking tension in the string. If the boy will move further from that point, this string will break down. Okay, so we have to find out that particular point up to which the boy can move without breaking the rope. The values are given: FM, weight of the boy, FP, weight of this board, and FT, that is basically the tension. Okay, length of the board, that is 6 meters, and length of the, you can say, the central point FP, that is 3 meters. So we will write down the given data over here. Weight of the beam, that is FP, distance of the central point LP, weight of the man 400 Newton, tension of the rope 400 Newton, length of the beam LT 6 meters, and the unknown value, required value, is distance of boy from point A. Let's say that we are naming this point as A, so we have to calculate distance of this boy or man from point A, LM. Okay, so we have written all the values which were given, and we have to find out the required value. So you can see a rough figure for that the boy, let's say that this is the point where the boy is creating the breaking tension in the string. If he will move further, this string will break down. Okay, so let's say we are naming this point as D, and this support is at point A, central point is C. Okay, so LP, these things are given, all these values are given. So you can see this is the figure where boy is moving towards that point. This is just a rough figure because we don't know that what is that particular point that will create the breaking tension. Okay, so again what we will do over here, you can see we are having just one unknown value, just one unknown is there, but that unknown value is the distance, so we cannot calculate that unknown value from first condition of equilibrium. So by applying first condition of equilibrium. There is no need of applying first condition of equilibrium over here, okay, that is useless. So we will just apply second condition of equilibrium. In this case, sum of all the torques is equal to 0. Therefore we are applying sum of all the torques is equal to 0 over here. You can see, if we take this support, this point A as the axis of rotation, then what will happen? This will create a torque in clockwise direction with M. This FB, that will again create a torque in clockwise direction, and this FT will create a torque in the anti-clockwise direction. Okay, so what will happen? We have to adopt the sign convention. Let A be the axis of rotation over here. Now for balance condition, let the weight of the beam is acting at central point C, weight of the man is acting at point D, and the torque due to FB. Now what we will do, we will find out all the torques separately and we will put them in equation number 1. Tau P is equal to LPFB. Okay, by putting values in equation 2, tau P is equal to FP and LP are given, so we will find out torque due to tau P, which is the torque applied due to the beam. Okay, that is 600 Newton meter. The torque due to FM, the torque due to man or the boy, that is tau M is equal to LM cross FM, but this LM is unknown value. We only know the weight of the man or boy, so we will just write it as tau M is equal to LM cross 400 Newton. So you can name this as equation number 5. Okay, we have calculated torque due to all the forces separately. Okay, the torque due to FT, the torque due to the rope, that will be given as tau T is equal to LT cross FT. By putting values in equation 6, we will get torque due to the tension in the string, that will be 2400 Newton meter. Name it as equation number 7. Now putting values from equation 3, 5 and 7 in equation number 1, what will happen? We will put all these values in equation number 1, then we will solve these values. Okay, after solving these values, what will happen? We will get the result. We will find out the length LM, the distance which the boy can move without breaking the rope. Okay, so by separating this, you can see we will separate out this LM over here. LM is 1800 divided by 400. Newton will be cancelled with Newton, and this length will be 4.5 meters. So the boy of weight 400 Newton can walk 4.5 meters towards the support without breaking the rope. Okay, so I would like to end my lecture with this quote: be aware of your own worth, use all of your power to achieve it. Create an ocean from a dewdrop. Do not beg for light from the moon. Obtain it from the spark within you. Okay, so be aware of your own worth. Use all of your power to achieve it. You have to follow this quote. You have to do it, because you can do whatever you want to. Okay, that was all for today's lecture. Thank you so much.